Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 4, in which we will be discussing factor experiments, one-factor designs, and extensions. So there is no R code for here, just this PDF and a short one at that. So in this section, we'll describe an experimental design to compare the effectiveness of 4 insecticides to eradicate beetles. We want to know which insecticide is most effective, and we'll measure that by which gives the lowest survival time for beetles on average. So this is a situation where we can design an experiment, and experimental design is an entire field of statistics, or subfield of statistics, where the considerations are: how do we best assign observational units to treatments to give us the most statistical power to determine the effects between treatments. And there's many ways of doing that. The most simple is here, the completely randomized design. So in this case, a scientist might select a sample of genetically identical beetles for an experiment and then randomly assign them to a predetermined number of beetles to each of the treatment groups. Even though the sample sizes of the groups need not be equal, that is often a preferable situation if they are equal. And a power analysis is often conducted to know how many observations do we need in each group. And of course, that sample size depends on how variable the response is for each group, which you often don't know before you conduct the experiment. So power analysis is a sophisticated strategy to take. So for simplicity, assume we've got 48 beetles, and we're going to assign 12 beetles to each treatment group for these different insecticides. So after assigning the beetles to the 4 groups, the insecticide is applied uniformly to all experimental units. In this case, the experimental unit is a beetle. And then the individual survival time is recorded. So you powder them with the insecticide, you start the stopwatch, and then you poke them every once in a while to see if they poke back. And when they stop poking back, you record the time on your stopwatch. A natural analysis of the data collected from this is a one-factor design, which is what we've seen last semester in Chapter 5, the analysis of variance. So the factors, or the groups, are the different insecticides, and the survival times is the continuous response variable. So when you design an experiment like this, you basically want all the beetles to be perfectly homogeneous, almost basically identical replicates of each other. So those are the controls that we're going to build into the experiment. We're going to choose a common strain of beetle for all the observations. We want to make sure that they're not genetically different or different in ages, or maybe even the sex of the beetle. Effectively, we would like, in all respects, every beetle to be the same. And then the variability that you are measuring is the difference between beetles, and so that ends up just being the minor differences in survival time for a very specific type of beetle. Then you've minimized the variability within each of your treatment groups, and you're most likely to see effects. Let's see. Furthermore, the differences you do observe, because there aren't any differences between beetles, must be ascribed to the treatment you provided. So in complicated or complex experiments, there are always potential influences that are not realized or are thought to be unimportant that you cannot control. So randomization is an important thing to do when you are assigning beetles to treatment groups. This will, philosophically, the argument is that if you randomize your 48 beetles into the 4 treatment groups, then it's assuring that there's no systematic dependence between the characteristics of the beetles and the groups that they are assigned to. So that when you then look at your 4 groups of 12 beetles, you can say these 4 groups are, for all practical purposes, starting off the same. Therefore, the differences we observe between these 4 groups must be due to the treatment. So that is largely what the rest of that paragraph says. So this is perhaps the most important sentence in the chapter. It's a definition of what an experiment is. And I think of this in terms of being 5 words. An experiment is to impose a treatment on experimental units to observe a response. If you miss out on any of those 5 things, to impose a treatment, experimental units, observe response, then you haven't done an experiment. In particular, if you don't observe a response, you don't know what the effect is. Experimental units are just, in this case, the beetles. It's whatever you are measuring. So a person might be an experimental unit. A school system might be an experimental unit. So it's just basically the smallest thing that you're measuring. The main parts of an experiment is the imposition of a treatment. For example, when you ask someone whether they smoke or not, the treatment is whether they smoke or not. And you observe a response on the experimental units, but because you did not impose the treatment of them smoking, that you have not conducted an experiment. You have simply observed natural behavior in the environment, or perhaps unnatural, given that it's an addiction that is manufactured. But the point is that is the distinction between an experiment and an observational study. And often that distinction is philosophically the difference between whether you can assign causality or not. If you conduct an experiment, then you can say, because you've performed randomization to assure that groups start off the same, that the only way to explain differences after imposing a treatment is that the treatment is responsible for the differences. If people choose to smoke, then there may be other lifestyle characteristics that go along with smoking that make them different, and so it's hard to assign causation from smoking to some other outcome or something else that could go along with smoking. Okay, so some notation. So suppose we've got Yij, and I should say I do want to focus a bit on models in this class and talking about writing models down and being able to explain models and a lot of things like that, because it will give you, once you start to develop some skill with writing a model down and interpreting it, you will find that you could write a model for almost anything, and it gives you a lot of power to make good decisions and to understand complex questions. So suppose Yij, so Y here is the response. In the case of our beetles experiment, that is the survival time. I and J are subscripts. They're going to each indicate a different piece of information. J is going to be the experimental unit, so that will count from number 1 up to 12 within group I. So I is the treatment group. Okay, so we have 4 treatment groups in the beetle experiment, and in each treatment group we have J, which goes from 1 to 12, enumerating the 12 beetles. And so this model goes along with the statistical design. We have one factor, the mu's, the mu i's, which is the mean for group I. So when you're in group I, we expect the observations Yij to be centered at the mean for that group, mu I, and that the individual variability around that mean is accounted for by Eij. Okay, so every observation is centered at the group mean, but then has its own residual. And we often assume that these residuals have the same distribution for all the groups. In particular, that the residuals are normally distributed, and that the variance is the same across the four groups. And of course that they're independent. And so we're going to treat beetles here as being independent, that the survival time of one beetle does not affect the survival time of another beetle. For example, they're not battling to the death as they're also dying from the insecticides. Poor guys, or gals, depending on how you controlled for sex. All right. So all that is what I gave as an example in this last paragraph here. So here might be the four distributions for the insecticides. Okay, so we have along the horizontal axis, we've got survival times, and we have these four normal curves. Notice that the spread, the shape and the spread of these four curves are the same. That's the assumption that the residuals are normal and centered at a different mean for each group. Okay, so if you center this last group where my cursor is, the residuals are the horizontal offset to the left or to the right of my cursor. And so those residuals are basically have the same distribution as this for group 2, which is centered at this point. That's the idea. All right. So there's several other ways to write this model. In particular, there's one way where you could write it in terms of including a grand mean. So if we let mu, notice there's no subscript, be the grand mean of all of the group means. Okay, so we have 4 group means where our insecticides, our survival times are, and maybe the group mean is actually maybe we're close to where the mean of the first group is. Okay, somewhere right around here. So that is grand mean mu. Then you can think of alpha I, which is called the treatment effect, as being the effect or the difference of each group from the grand mean. So for an average, in quotes, for an average insecticide, an average beetle will survive mu, length of time. But if you have a specific insecticide, I, then they'll survive either longer, in case mu I would be greater than mu, so the alpha would be positive, or it could be shorter, and alpha would be negative. If you define this in this way, we have this constraint that the alphas have to sum to 0. Okay, all these mu's are centered at, all these mu i's are centered at mu. Because you've constructed the mu out of the mu i's, we have this constraint that the differences must add up to 0. Okay, not a big deal. So here's an alternate way of writing the model that I had before. So let me page up for a moment and bring up this model. Okay, so here's mu I, and I'm going to just replace mu I by what mu I is in terms of the grand mean mu and the treatment effect alpha. So I'll page down. So if I solve this equation for mu I get the minus mu goes on to the other side, so I get mu plus alpha I is mu I. So here's the same model, but it's written in terms of the grand mean, and we have these alphas, which are the treatment effects. All right, so in words, the response is the grand mean plus the treatment effect plus the residual. And in analysis of variance, where we ask under the null hypothesis, are the means all equal to each other? that's equivalent to asking whether all the treatment effects, alpha I, are equal to each other and that equals 0. If the null hypothesis is true, that all the mu i's equal 0, or equal each other, excuse me, or that all alpha i's equal 0, then this model simplifies to all the beetles come from a distribution with the same mean. All right. This last paragraph simply says there's different ways of, there are those two ways of modeling this, and they're equivalent, and it really depends on the software how you do it. In particular, when we fit models in R, let me page up for a moment. R uses this specification of the model. No, my apology, page down, page down, page down. R uses this specification of the model. It specifies mu as the intercept, and then alpha i's are the differences from the intercept. But it forces a slightly different, it forces a third notation that is not shown here. SAS does the same thing but in a different way. SAS is another software. R specifies the first treatment group. It sets the alpha equal to 0, which makes mu the mean for the first group. And then groups 2, 3, and 4 are the differences from that first group. So that's a third way of specifying the model, which is different from the two ways that we just saw. The only real important difference in the different ways of specification, for example, what I just said was this is how R does it. It sets alpha 1 to equal to 0. SAS uses alpha I equal to 0. It makes the last group the baseline group. The main difference, or the main importance here, is how you interpret the coefficients. So if I scroll up for a moment, making those different choices makes alpha I mean something different. When mu is the grand mean, alpha I is the difference from the grand mean. When alpha 1 equals 0, meaning that the first group is the baseline group, then the other alpha i's are how different each group is different from the first group. So knowing what the software does allows you to interpret the model appropriately. Okay, that was a lot of words. Let me just come back to this. That is the most important sentence in the chapter. An experiment is to impose a treatment on experimental units to observe a response. Next up, Chapter 5, where we'll do some modeling with factors.